So all that being said, regression. So the nice thing about this chapter is it's basically the last chapter on steroids. Right. So regression is a more formal version of correlation in a sense. So the difference is prediction versus relation. So with correlation, it's all about, are they related? Do they go up together? Do they go down together? And I said we don't really pick an X and a Y, an IV and a DV, because with correlation, the idea is that we don't know which direction it goes. With regression, we are suggesting the relation. So I still don't say that it's causal, because causal depends on the research design, and most regression designs are not causal. But I am saying I expect this one to be first theoretically. So I expect smoking to cause cancer. So I'm using that as my predictor for my criterion, A or Y. So the big difference here is in regression, I pick one to be the cause, even if the design doesn't allow me to say it's causal. I pick one to be the first event and one of them to be the effect. So it is a statistical tool. It's just so cheesy the way they write these, but it lets us predict someone's score on a DV based on one IV. That's simple linear regression. So see the simple out here. So simple is one IV to one DV. That is mathematically the same as correlation, which you'll see in a little bit. Multiple regression is where it gets more useful, where I can use more than one IV to one DV. So one IV, one DV, simple regression. Multiple IVs, one DV, multiple regression. Multiple of both, structural equation modeling.
Is that where you start getting into like Euclidean distance and things like that?
Yes, Mahalanobis is technically multiples.
So it would be like multiple dimensions then, kind of, if you were to think of it on a graph.
Yes, it is.
That's terrifying.
Yes. Okay. So let me draw this. With regression, let's say we have a bunch of dots. So the number of emails I've gotten this morning and my frustration level. Right? Because so I've gotten probably like 50 this morning already over nothing, to how frustrated I've gotten every time my phone buzzes. Right? So I would expect that to be positive unless someone's offering me money, and then it might go down. But if we were to add a line to this equation, that's the regression part, is adding the line. So A here is the intercept. We're not going to use mx plus b, sorry, we just don't. Okay. So A is the intercept, so here's probably about 0. So no emails, no frustration. It's also the mean of y. So the y-intercept is whatever the mean of the y is without any x's. So I guess it should be a little higher. Is this the end of semester? I don't know. B is going to be our slope. Here. So for every one email, how much frustration do I go up? So the interpretation of B is for every 1x, y increases B points. Points as an N. There we go. So for every one email, frustration increases. If B was 2, it would be 2 points. So sometimes that's called a coefficient. In the output, I think we're going to see today, it's going to be listed as coef, I think, pretty sure. Either coef or estimate. It depends on which one we see. And really, B is a weight. So how much do we weight X to predict Y? So if we start adding extra X's, it's how much they're weighted individually. So how much does this one matter contributing to Y? Because the point is to figure out the best equation, or the line of best fit, sometimes called, for predicting Y. So the closer the dots are to the line, the better we're predicting. just like with that correlation game we were playing, where the closer the dots were together, the higher the correlation, same idea. The closer they are to the line, the better the fit. Don't close it all the way, it'll be... They still haven't fixed it. So here's an example from the book. That would be a perfect equation. So every dot's right. That never happens. But 5 would be the y-intercept. Slope is about 7 points. I think throughout this entire semester you've seen that we really love standardizing things. T, F, Z, all standardized. Standard deviation, standardized. I mean, what haven't we done that isn't standardized, right? So we love to standardize things because being able to compare across different scales, across different test types is important. So we're also going to talk about beta. So if we standardize the equation from a plus bx, the a drops out. Okay, so when you remember when you z-score things, the mean becomes 0, so we just drop it. And then b becomes beta. Now the nice thing is that with one x and one y, beta and r are the same. So beta is the z-score. Remember, r is the z product of z. And we do that so we can compare. So with one predictor, beta is like only marginally useful. It's kind of like, here's an r. With multiple predictors, beta allows you to compare them together to each other. Because b is unstandardized. So b is in the original scale of the data. So let me give you an example that'll help make that clear. Let's say we're trying to predict your final course grade with attendance. Well, that's going to range from 0 to 45. We have about 45 classes. Right. Your previous GPA, that only ranges from 0 to 4. Your ACT score is 0 to 36, right? If I remember correctly. Yeah. What else can we throw in there? Socioeconomic status, that's got a big range. First year gen status, that's a yes or no. So you see how all of those have very different scales. B, for each one of those, is going to be in the original scale. So GPA's point scale thing is going to be really small because it can't get bigger than 4. Okay. What beta allows me to do is put them all on the same scale and compare them. So which one of those predictors was most useful? So that's why people use beta. Plus, we just like standardizing things. It's like a thing. Like, oh, z-scores are beautiful. So we're going to try one. Yeah.
So in the equation, just very quickly, what would y be defined as?
Y is the dv.
dv. Okay.
Oh, I didn't tell you what y hat meant. Sorry. Let me redraw this. So we're going to pick 2 columns from the giant RP4 data set. And I was hoping this might answer some of your questions. My favorite 2 to correlate are positive emotion, which is posimo, and negative emotion. But we can pick other ones. And we're assuming you're probably going to have a negative relationship, because as one goes up, the other should go down. So each one of these is y. Your actual score, so if we go back to my example, your score in the class is what we're trying to predict. We're not always perfect though, so sometimes we guess that you're here, and that's y hat. So y is your actual score, y hat is your predicted score. And we're doing this. So this is the intercept, d is the slope, x is the IV, this is the dv predicted. A lot of the questions on the homework end up being, if somebody has a, there's a jury one. If the jury's been deliberating for 10 hours, what do you expect them to do? Right. So you just plug in the numbers they give you. So let me pull up that data set. It's a giant data set. Excel was not happy with me making this. There it goes. Okay. So if we just kind of look at the columns, so clout might be kind of fun. But if we pick positive and negative emotion out here, throw those into a new data set. I'll upload this for you guys real quick. There it goes. So you would get rid of, like for your research project, you would get rid of the other groups if you weren't interested in the other groups. So delete those rows and the other columns that you weren't interested in. Don't try to load that whole thing into R. I mean, you can, it'll just make your computer unhappy.
This makes more sense.
God bless Blackboard, but ugh. There we go. Submit. Okay, so if you go to the notes page and hit refresh, you should see that file with positive emotion and negative emotion in there. So given that, do we have random selection? Nope. I mean, somewhat, maybe. I don't know that everything had an equal probability of being selected, since we had specific search terms, right? And we certainly didn't randomly assign. So in a lot of correlational research, those two are going to be no. You just can't. Are X and Y at least scale? Yes, they're percentages. So they're ratio. There are zeros, and they mean no words in that category. Are they both normal? Oh my gosh, we get to say yes. Don't really know, but we have at least 30 people. Yay. And then homoscedasticity, just like we talked about earlier this week. For that, I'm going to have to make a plot. So we'll take all that plot code we did last time and make a plot here in a second. So I'll come back to that. So just like with correlation, where it was the correlation between this and this is 0 or is not 0, it's the same idea, but now we're talking about B. So with step 2, it's positive and negative emotion are related. So B is not 0. For the null, positive and negative emotion are not related. Or B equals 0. Which is the same thing I have here, I just have it back. So the people where the IB does not predict the DV, so B is 0. The people where it does predict, and this is more formal. So no relationship between positive and negative emotion, B is 0, or there is a relationship. It is much easier if you don't pick a side. And I could do a one-tailed test. I could say I expect B to be positive, so greater than 0, or less than or equal to 0. But correlation and regression, it's just always easier if you pick a two-tailed test. because random stuff happens sometimes. Alright, so that's the same as correlation, except this one's B and not R. So for step 3, we're going to get the regression equation. So we're going to fill in A and B. We're going to come up with degrees of freedom. Still n minus 2. 1 for x, 1 for y. And then let's try that and make our plot. Okay, so before we do the equation, let's load up the data set. So import data from text file. Hopefully this part's a lot easier. 58,000. Oh goodness, I forgot how many lines I had. So degrees of freedom are going to be 50,432. We've been working with what? 15, 10, 8 all year. Yeah. So this is more normally what we do in the lab, where we have these huge data sets that are just sitting there waiting for it to load. Right? And that's one reason why I don't load this entire data set into R. Your computer can probably handle it. It's only like 30 megabytes, but it will be easier if you just get rid of everything else first. Once we have that loaded, I'm going to go open the chapter 15 script. Because it has all the plot stuff at the beginning. And I'll make a new 16 script and upload it for you guys. That was much easier to open than to type all that again. So if you're on a school computer, don't forget you'll have to install ggplot first. I know, it's annoying. Okay. I'm going to load all my theme coding so to get a pretty plot. And we've got my plot equals, so the first thing is the data set. The second thing is the name of the columns. So I can do this in either order. What you always want to do here for this one, where it says AES for aesthetic, and where it's column 1, column 2, put X first. So whichever one is they label as the predictor in the question. For me, I don't know which one I'd really expect to be the predictor. Like, would I expect like more positive emotion? Actually, most of these are really negative. So we might expect that the amount of negativity would predict lessened positivity, but we can do it either way. But when you are reading the questions, like on the homework, they have the very specific, this one is X, this one is Y. Okay, so put this one X first. I'm going to change my X lab here to positive, and my Y lab here to negative. Let me try that. Let's see what we get. Oh boy. This is not quite what I was expecting. It is a sunburst. Alright, so there are a lot of zeros. And that's something you might consider too for your question, is to delete the ones that have zeros and only compare data sets that even included the words you were interested in. Because of the way we process the data, sometimes it just didn't have the words you were interested in. But at the moment it is an interesting sunburst. So do we meet the homoscedasticity assumption? That's a big no. Right? It is a perfect example of the megaphone effect. Right.
So when you say delete the ones with zeros, do you mean delete the ones with both zeros?
Both zeros.
Okay.
Yeah, so if it doesn't contain any of the words you're interested in at all, that might help make it less messy.
Is there a script you can use to do that?
To do that? Yeah.
No, seriously.
I can show you that right here. Yeah, you could also sort in Excel, but let me think. Where
Let's
they're
do it art our friend.
both zeros. Okay, so I'm going to save it as a new data set. You're making me do something on the fly here. Subset function. And then it's data set name. You don't have to do this. Okay. Comma. And then the rule. So I want column 1 is greater than 0. Right, it's a posimo. And column 2 is greater than 0. I think that's going to delete everybody who's got a 0. Wait, no, don't do and, do or. Or is that straight up and down pipe thing? It's above the enter key. Where at least this one or that one is greater than 0. Fingers crossed I have that right. Oh, I think it did. That deleted 20,000 lines. So some of them still have zeros, but at least one column has something in it. That's one way to do it. And I can help you do that for your RP4 if you want to do that.
Our wizardry.
Double subsetting is something I don't even think my other class totally gets. So if y'all get that, I'm going to be like happy camper. Anyway, let me try making the plot with the new data. Did it change? It had to have changed. What just happened? Oh, clicking. It moved slightly off of 0, but it's still pretty bad. Right. Hold on, let me hit the broom just to make sure that the plot actually looks the same. Yeah. So what happened is that we just cleared out this little spot. Here. It still looks bad. But conceptually, if you think about it, if the data sets that you're interested in don't contain any of the words you're interested in, it makes sense that you could delete the paragraphs that don't have any of those words. We've done that for another project of ours. So known homoscedasticity. That's what that was about. How do I get the equation? I'm using a new function. It's called LM. LM stands for linear model. Okay, that's regression. When we ran the ANOVAs, the easy ANOVA stuff, it was doing LM in the background. Okay, so we've actually used this function, you just don't realize you have. So we're going to save the output. I'm going to call it easy default output. LM stays. The DV name in this case, let's make it negative emotion. Tilde, positive emotion. Data, wherever the data saved. And I called it new data here. Just so it's clear why that's in there. Okay. All right, so output equals, I got LM. I do negative emo. Tilde, it's above the tab key. Posimo, data equals, and then the data set name. Oops, I said new data. Sorry. I got excited. So what's happening is you're setting up the equation. We said y equals a plus bx, right? So this is y is approximated by x, and it's going to figure out a and b for us. So that's why the format is y is approximately x. So the tilde means estimate. So estimate negative emotion using positive. And then as a quick foreshadowing for Monday, if I wanted to add extra columns, I just do plus, positive emo plus something else plus something else. That'll save all the output over here under output. But there's a ton of crap. If you click the little down arrow on output, you'll notice that there is a lot of stuff. You don't want to see all of that stuff. So just do summary of the output. Just give me a summary. And this, oh, I'm sorry. Summary like that. And then you should get this. I'm just going to put this in a word to make it a little bigger. So summary of the output just like this. Now, if I'm trying to figure out what's the equation, I'm trying to get a lot of stuff here, but we're really interested in this right here. So it says estimate, it's the other function that says coef. So I've got the one that's clearly labeled intercept. That is nice. Okay. So that is A. So y is approximately 6.78%. So that's the average of y. The average negative emotion, if we exclude the zeros, is 6% of the words, which isn't too surprising given the types of questions we were looking at. Minus, so it is a negative relationship, although that graph does not look negative, 0.44. I'm going to throw an X here. So negative emotion is approximately 7% minus 0.44% for every 1% of X. So every positive word, we lose 0.5% on the negative words. So that was the direction I would have thought. The graph does not portray that clearly. Right? So that's what I mean by filling the equation. So it's A, and if you can't really tell or remember, it's in alphabetical order. A and then B. Degrees of freedom, it's actually right here, but it's in -2.
And we removed a bunch of columns for new data.
Right, so that's why it's 35,000 at the moment. So here, so it's our 35,339, but also on the output, it's this number. Okay, so we've looked at these two. Okay. Here, so our DF, 35,337, giant number. But we're also going to talk about how to get beta. Really, beta is going to be more important for the next section, but I just figured we'd do it now. So what is beta in this example? So you'll want to install the quantpsych library. Fortunately, it's pretty easy, but unfortunately, we have to install the package. Because I don't think we've used that one in this class. And then nicely, it's just lm.beta, once you get it installed and loaded, of your output. So whatever you call the output here, right, not the data set, the output, use that again. That's why we saved it, so we can use it a couple times. So lm.beta. It just gives you beta, no fancy nothing. Like it just says like, here's beta, done. So it's negative 0.35. At the moment, that is R. So effect size wise, this is how it's a medium effect. Right? So remember the rules are 0.1, 0.3, 0.5. So that's a medium effect size. Even though the graph is super messy. And so we got beta. On Monday, we're going to do multiple regression. And we'll have multiple betas, so we'll be able to compare them. The issue is that don't totally think beta is R. Because in multiple regression, beta is not R. It's only in single regression. Because then it really confuses people when they get a beta of like 1.5. They're like, what did I do wrong? I'm like, nothing. It's just not R when you have more than one. So let's finish out these 3 steps, and then we'll save the rest for next time. So step 4 is the same as correlation. It's our QT function. So we're going to do QT 25 divided by 2, our crazy degrees of freedom. And the lower tail is false.
So what would be the name of the, like, so we've had Z critical and T critical. What's the name of this one?
It's still T critical.
Still T
It's
critical?
It's T, yeah. The only time we've used F is for ANOVAs. But remember, F and T are cousins. So yeah, it's still T critical. So remember that as you have enough participants, right, these are paragraphs, T becomes Z. Remember, it says it's about 100, T becomes a Z distribution, and 0.05 was the cutoff for Z was 1.96, so we got 1.96. So we've approximated Z at the moment. If we were using F, we would just square that. So with a data set this large, T and Z are the same. So we got 1.96. Well, where do I get T? It's in that output. So T found. It's right here under T. Oh my God, it's 70. Wow.
Good job.
That's unusual. So I'm definitely going to reject it. No, all right. So here's another sort of tip just for the test. If it has stars out here, you're going to reject. Just be careful. Don't use the intercept line. I'm not really interested if the intercept's greater than 0. Sometimes you can be, but right now we're not. We're just interested if X predicts Y. And this is X predicting Y, and it's got little stars, so it's significant. At 0.05, right? It gives you what the stars mean down here. And the reason that's so large is because the data set is so huge that the standard error is really small. So here's standard error right here on the output for you. So SE is really tiny because we're dividing it by 35,000, square root of 35,000. It's very small. Yeah.
Why is there a T value for your intercept?
It does test if the intercept is greater than 0.
Oh, okay. So it'll actually tell you what basically Y bar is without.
That is a single sample T, essentially. So this is 6.78 greater than 0, which is a single sample test.
Okay, that makes sense.
But in regression, that's not always a question that you're interested in.
Okay.
Like, do I care if the percent of negative emotions is greater than 0? No, I could care if positive predicts negative.
Okay.
So that's why I'm ignoring it. Okay, so that should get us all the way through the steps. The last little thing, without totally explaining it, just since we have the output up, is the effect size. And we're gonna start here next time and go into this more because there are more slides about how this works. But our effect size could be R, but since we're gonna talk about multiple stuff on Monday, we're gonna talk about R squared, and it's capital R squared, which is the same thing we did for ANOVA. So it's 0.01, 0.06, 0.14. Now, R squared is the proportionate reduction in error, which is totally a discussion for, on Monday. Oh, well, better than Friday, I guess. So R squared is my effect size. It's the reduction in error. So it's essentially, as I use X to predict Y, how much better is that than a random guess at Y? And the reason I wanted to mention it is because it's right here on the output under multiple R squared. 0.12, it's close to large.
Is the adjusted R squared, is that after adjusting for width and groups variance?
It's a long story.
Okay.
It's a mathematical adjustment for population size. So you'll notice how they're not different on this because the sample size is so large.
So big, yeah.
So it adjusts for sample size.
Yeah.
We don't use it.
And since does the adjusted R, is that basically always going to be the same if it's larger than 100 because of the T thing?
Pretty much.
Yeah.
Not perfectly. Depends on how big the error is too. So it's adjusted for a bunch of things. It's
Okay.
really more complicated than I care to think about. But use multiple R squared, don't use adjusted. Okay. So let's stop there and let me answer some